Alrighty, y'all. Today we're looking at question 7 for homework number 2. And for this one, we're trying to find the height that a proton is going to be accelerated to by the electric field from a infinitely thin sheet so that it reaches a velocity of our speed of light here, 3 times 10 to the 8th meters per second. So I'm just going to draw a quick picture just to visualize this. This is going to be our infinitely thin sheet looked at from the side. So we're pretending it is infinitely thin, and I can draw that. That's going to be our proton. And that's going to be at initial height of 0.02 meters, which is our starting point with our 2 centimeters, but in meters. Because again, keeping all of our units consistent is very important. And it's going to be accelerated to this height, starting, here's our 0 here. I can write that better. That's going to be accelerated to some height, r2, that we're going to solve for. So since we're talking like speeds and velocities, it's a pretty good clue in that we're going to be talking about our law of conservation of energy. So that means that our initial potential energy plus our initial kinetic energy is going to equal our final potential energy plus our final kinetic energy. Now, since we're moving up and down and all this stuff, we're not just going to have a change in our electrical potential energy, we're also going to have a change in our gravitational potential energy. So I'm just going to move this over so I can, here's our electric initial plus our gravitational initial. And it's going to be the same thing on this side. It has to be our electric final plus our gravitational final. So these two together is going to give us our total potential energy, but just individually they have different equations, so we're breaking them up. And now for this, the first thing I'm just going to do is I'm going to take this initial and subtract it from both sides to move it over this way. So I have my gravitational initial plus our KE initial. It's going to equal our final minus our UE initial. So I just subtracted that over, plus UG final plus our KE final. So if you just look at this, that's just going to be final minus initial. That's just our delta U, electric. And then so that's plus UG final plus KE final, and UG initial plus our KE initial. Those are equal. So now that we have all of this, we get to start plugging in our known equations, right? Our known, what we're eventually going to be solving, right? So we know that our kinetic energy is 1/2 mv squared. So our initial is going to be 1/2 m times the initial velocity squared. And since it's given that it's released from rest, our initial velocity is just going to be 0. So our kinetic energy is just going to go to 0. And then our equation for gravitational potential energy, that's just mg. And then our h, since we're starting, this is our initial h, it's going to be 0.02 meters. And that's going to be equal to our equation for our change in potential energy, that's negative integral from R1 to R2 of Q electric field dot dr. That's going to be plus, again, our mgh. This is going to be mg, and like I said up here, this is our R2 up here. And our R1 is actually, our R1, right? So where we're starting from, that's going to be our 0.02 meters as well. And that's plus the 1/2 m v final, 3 times 10 to the 8th squared. And that's just because it was given in the problem that we're trying to get to that velocity. So now that we have our equation all set up, I'm going to start looking at some of these pieces inside this integral, right? So if we go back to our initial position, the electric field from this plane is going to be going up this way. Because since it's a positive surface charge, it's going to be going up that way. Our radius is here or here. Those are our the highest and the lowest radii that we're looking at. So those are going in the same direction. Since they're going at the same direction, the angle between them is going to be 0, and cosine of 0 is just 1. So when we're dotting these two vectors together, it's just going to be the magnitude times cosine of 0, which is 1, so it's just going to be multiplying the two magnitudes. But what's the magnitude of our electric field? that's just what's caused by this infinite sheet here. So we're going to estimate it with the infinite sheet. And we have the equation is that electric field equals sigma over 2 epsilon naught. And we're going to plug that in, and that's going to give us this lovely mess of an equation. That's mg times 0.02 equals negative integral from, I'm going to move you out of the way, integral from 0.02 to R2 of Q sigma over 2 epsilon naught. I just multiplied that Q in there, dr, because again, that's just the magnitude of that radius vector, plus mgr2 plus 1/2 m 3 times 10 to the 8th squared. All right, so now we have this whole equation that we're trying to solve. Our next step is to actually take this integral. So all of this mess in here, our charge, our surface charge density, our 2 and our epsilon, those are all just constants. So we can pull that out, and if we're just taking the integral of dr, that's just going to be r. So what this integral is going to look like is just going to be negative q sigma over 2 epsilon naught times r, with that r being evaluated between 0.02 and our R2. All right, so now if we plug in those bounds just real quick, it's going to be negative q sigma over 2 epsilon naught times R2 minus, but since that negative, this negative here is going to be distributing in, because it would usually be R2 minus 0.02, but since it's negative, it's going to be plus q sigma over 2 epsilon naught times 0.02. All right, and that's just in the middle of this whole other equation, m3 times 10 to the 8th squared mg 0.02. So that's just that in the middle of that equation. Now I'm going to move all the constants, anything that doesn't have an R2 in it, I'm going to subtract and move over to this side. So I'm not rewriting everything, I'm just going to literally move things. So we're going to have this minus this, get rid of the plus sign, but minus this, minus this, that's going to be equal to this plus this. Cool, efficiency. Now I'm not going to rewrite the entire left side, but I'm going to factor out this R2 from the left, and I'm going to just switch the order. So instead of, so just the negative is going to be on the other side. So that's just going to be R2 parentheses mg minus q sigma over 2 epsilon naught. Now to isolate this R2, I'm just going to divide both sides by this. I'm going to divide it over here. So what it's going to end up being, because again, I don't want to rewrite all of this, it's going to be this whole mess divided by this whole mess is going to equal R2. So that's going to be our equation to solve for R2. And if we plug in, we only have constants left, because we have the mass. The mass was given in the problem to be 1.67 times 10 to the negative 27. 1.67 times 10 to the negative 27, and that's in kilograms, which is very important because, again, we're keeping everything consistent units. That G, since we are keeping it in consistent units, we can use our G equals 9.81 meters per second squared. Our Q, that's going to be the charge of the proton, and since it's just the proton, that's going to have a charge of 1.602 times 10 to the negative 19th coulombs. Our sigma, also given in the problem, is just going to be 1 coulomb per meter squared. Then Then we have our epsilon naught, which is obviously the constant 8.85 times 10 to the negative 12th. And that's all of our variables in there. Everything else is just numbers. So you're going to punch all this into your calculator, and you're going to get the answer for R2. The answer you get, since we kept all of our units consistent, is going to be in meters. So I think all the answers on Kudu are in centimeters. So you just convert that into centimeters and make sure you have the right units. And that's just going to change your order of magnitude. All right. So thank you very much for watching. I hope you found this at least a little bit helpful. Let me know if you have any more questions about this problem, or if there's any other problems that you want to see me work out at all. I'll do my best to explain them, because I guess Sydney explains stuff.